Hey, what's up, guys? This is Cheng here. So, LeetCode 1906 minimum absolute difference queries. Okay, so the definition of minimum absolute difference of an array A is defined as the minimum value of any two elements in this array uh, where the value is different, right? Because if all the elements of A are the same, and then the minimum absolute difference is -1. Basically, if everything is the same, instead of 0, right, we want to return -1. So for example, the minimum absolute difference of this array is 1, right? Basically, we have 2 and 3, right, can give us the minimum difference, which is 1. But keep in mind that 2 and 2 is not, right? Because like I said, so if we only have 2 and 2, we'll return 0 in this case. That's why the 2 and 2 will not will not count as a valid pair here. Okay, and that's the definition of this. And then you're given like integer arrays nums, and then another array queries, right, where have a left and right range, right, and then you just need to, for each queries, you need to compute the minimum absolute difference, right, for this subarray from left to right. And yeah, so that's pretty much it, right? So for example, we have numbers 1, 3, 4, 8, right? So the query, we have like 4 queries. So the first one is 0, 1, right? So which means we have 1, 3. That's why the difference of these two numbers is 2, and then 1, 4, and 1, so on and so forth. Okay, and yeah, so that's it, right? And then here's like another examples, right? So for example, why we have -1 here, because from index 2 to 3, we have this 2 here, right? So for this array, well, we should have -1. Cool. And yeah, constraints, right? So the length is 10 to the power of 5, but look at this one, right? So remember, we have this kind of a pretty small number range here. This gonna help us in the later on. Right, cool. So for this kind of query problems, obviously, it will not it does not it's not expecting you to solve this one in a brute force way, which means that for each queries, we'll search the entire array this range from left to right, and then we keep checking, and then somehow I guess we have to find uh, the two closest items, right? So which means probably we will need to maintain I think most probably we need to sort, right? We need to sort this array, and then we're gonna find the minimum difference between two adjacent items, right? But that would definitely TLE, because given the length numbers here, right? By only querying the each range will make this solution of n square, right? That will definitely TLE. So, and then we have this kind of smaller number range here, right? So which can give us a big hint, right? Which means we should on top of this number here, we should loop through the numbers instead of the length of inside each number, but we should enumerate the values of the numbers, right? So what does it mean? It means that given like an array, right? Okay, given like an array, let's say we have some numbers, right? What we can do is that we can simply check the numbers from 1 to 100 at most. So we basically we check if each of the number exists in this array here. If it exists, then we know, okay, that's gonna be the one numbers, because the reason being is that since we're checking the numbers from smallest to the biggest, so naturally we are simply just scanning this will eventually scan every adjacent numbers, right? Because for example, if this one is like 1 1 1 4 and then 7 8 and 4 8 11 1 7, something like this, right? So by looking at the 5 numbers, we know the answer is 1. It's between these two, right? So if we scan the numbers from 1 to 100, or it's not 100, or the maximum number of these numbers, in this case is 8, right? So if we scan from 1 to 8, then every time if we can tell if this number exists in this array here, then we're as if we're simply scanning each neighbors, right? This is like, I think this one is similar like line sweeping stuff, right? So with 1 2 3 4 5 6 7 and 8, right? So in this case, we're as if we are like sorting this array. So this is also like a little bit similar to bucket sorting, right? So here one is here, right? 2 is not here, and then 3 is not here, but 4 is inside there, right? So now we have 2 adjacent numbers, so we can keep track of this, right? And then 5 is not there. 6, okay. I think I'm sorry. So we have 11 here. Okay, I thought this is a different one. That's why this one is 11. So this one is gonna be 11 in the end, right? So this one is not 7 and 8 and then 11, right? So as you guys can see, if we scan everything from 1 to 11, and then we can easily find those 2 adjacent numbers, right? So now the problem is that how can we efficiently find if a certain number exists in the array, right? Or in a range of array. Obviously, we cannot simply scan the array, right, to check the array one by one, but because that will go back to a O of n time complexity, right? So to check if an item number exists in the array here, we have 2 options here. There are 2 solutions. The first one is that we can use prefix, or we can use binary search. Sorry, the prefix, not prefix, the pre-sum. So, and the pre-sum has like a better time complexity comparing to the binary search, because the pre-sum can give us O of 1 time to check if an item exists, in comparing to a log n for the binary search. So this time I'm going to use the pre-sum. Okay. So for example, if we have 4 8, right, 1 2 3 4 5 8, right? So for example, if we have this kind of array here, so let's say we have a range of this one to 5. This is left and this is right, and we're looking for 4. We want to check if 4 exists in this array. So how can we quickly find that? Because remember, we're doing this queries for this search for each of the query. So instead of searching, looping, scan everything from here to here, what we can do is that we can do a pre-sum. We can do a pre-sum of 4 in this case. Actually, we need to do a pre-sum for all the numbers, but in this case, since we're searching for 4, right? So if we have a pre-sum, the pre-sum for 4 at each of the index, and then we can simply use this pre-sum to quickly find us if this 4 exists in this range. Because if we do a count by the index here, from 0 we have 1, right? And then from 8 we have 1 as well, right? So here it's 1, 1, 1, and then here we have 2, right? Here we have 2 and 2. So what we can do is that we simply just use the presum, or presum right subtract presum left. If the answer is greater than 0, then obviously we know there has to be at least one number in this range, because it could be 2 numbers, right? In this case, we're gonna have like 2, 2, and then 3, 3, and 3, right? So if we do a presum subtract, 3 minus 1 will be 2. So because as long as the subtract the value is greater than 1, then we know. So there has to be a number in this range, right? So that's a small trick by using the presum to quickly check the existence of a number, right? So now we have solution, right? So basically, at each of the index here, we're gonna have like a nested a list, right? Who has the length or the size of the maximum numbers, because at each of the index, we need to maintain the presum for all the possible numbers, right? And then we simply just use the presum to check if the number exists, and then we also keep track of the minimum difference, right, while we're scanning from 1 to this maximum number. And that's it, right? So that's the logic here. And then let's start coding. First, we need a max number, right? There's gonna be a max of numbers here. And then we have n dot length of numbers, right? And then for the presum, right? And so for each element, it's gonna be a size maximum number list, right? So at the beginning, we're gonna start with 0, right? So this time I'm going to use a list instead of dictionary, because this one is it's a nested. The element is a little bit complicated, right? It's not a single number. That's why I'm going to use a list instead of dictionary of dictionary. I believe you can also use dictionary, but I'm just sticking with my original approach here. So we need to initiate, when we use the list here, we're gonna prefix this array with 0 in this case, right? But since the item, like I said, it's another list, which means at the beginning we're gonna have like a list of zeros with a size of the maximum number plus 1, right? So that's gonna be the starting point. And then for num, in the nums here, right, we're gonna accumulate on top of the previous index. So that's why we're gonna make a copy, right? Current sum at the pre-sum of -1, and then do a deep copy, right? And then the current sum dot number, right? That's gonna be the ones we're going to increase by 1, and then we are going to append this new sum to the end of the pre-sum. Okay, so now we have a pre-sum, right? List of list, and we can enumerate the queries now. For left and right inquiries, right? So we're gonna maintain the current minimum difference. So at the beginning, it's gonna be a system dot max size, right? And then we're going to keep track of the pre one is -1, since we're going to compare the two adjacent numbers, right? So for num in range of 1 to max num plus 1, right? So the count, right? So count is going to be the pre-sum of, so the index is r, right? So since we prefix this pre-sum by the 0, that's why we have to increase the index by 1 when we calculate the range sum, right? It's going to be r plus 1 minus pre-sum of l, right? Otherwise, if we use the dictionary with -1, and then we're going to have r minus l minus 1, right? Oh yeah, so this one being the second index here is going to be a number, right? Because we are trying to check the count for this number. in this range. Okay, and then if the count is greater than 0, then it means that okay, we need to track this number. So if the pre is not equal to -1, then it means that okay, so we got a two adjacent numbers, right? So we can compare, we can update the minimum. The minimum of absolute difference. Actually, it doesn't have the absolute difference because we know the number is always increasing in this case. So it's going to be a number minus pre. Okay. Then we update the pre to the current number. Right. That's it. So that's the answer.append the minimum in the end, and then in the end we return the answer. I think that's it. But there's one thing we haven't covered yet. It's the -1 case, right? So what is the -1 case? -1 case means that everything within this range are all they're all the same. If they're all the same, it means that we'll only be enter this for loop once, right? Because there will be only one number exist in this range here, and if that happens, and so what it means that the pre at that time the pre will be -1, and yeah, so which means the minimum will never be updated in this case. So which means if they're all the same, the minimum will stay as the system max size. So we can just simply do this. So if this, we only return the minimum if this minimum is smaller than system max size, right? Otherwise, -1. So I think that's it. So if I run the code, okay, accept it. Yeah, there you go, right? So passed at least. It's because we have so the time complexity for this one is the query. Yeah, so this is an n, right? So we have a n times 100 in this case, right? Yeah, I think that's it. So for the binary search, right? So binary search is similar as this one. So instead of accumulating the count, we are like creating for each of the, I guess, so in that case, for, let's say we have 4, 1, 2, 3, 4, 5, 7, 8. So for binary search, instead of accumulating the count, we're gonna have, for each of the numbers, we're gonna have like a list of indices for this number. So in this case, let's say we have another 4 here, right? So we have 0, we have 1, 2, 3, we have 4, 6, 4, 5, 6, 7. We have 7. So for 4, we have a list of 0, 4, and 7, right? And then with a given range here, right? So for example, it's L and R here. I guess we can simply search, do a binary search of, do a binary bisect left on the L and bisect right on the R. So, and if L is smaller than R, then we know there's like index in between, because for example, if this one is like 0, 1, 2, 3, 4, 5, 6, right, 7. So if we do a bisect left on 2 here for this one, the index we get is what? So index 1, we have 1, right? So it's going to be here. And if we do a bisect right on the R here, which is 5, right? And if we have a 5 here, it means that it's going to be this one, right? So it's going to index 2. It's going to be 2 in this case, right? That's why since 2 is greater than 1, then we know because there has to be a 4 right in between, right? And what if the let's say that the L and R is here. So let's say this is the range, a new range, L and right, right? So for this one, if we do a bisect left on R, still we have 1, right? And if we do a bisect right right on R, which is 3, we also have 1, right? And if they are the same, of course, there's no index, no 4 in between, right? So this is basically a brief explanation for the binary search, and you guys can implement it if you're interested. But this one, as you guys can see, it's going to be a log n, right, instead of 1 time complexity for each of this 100. Yeah, I think that's pretty much it is for this problem. Yeah, I'll stop here. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye-bye.